Hello, welcome to my YouTube channel. My name is John Olafenwa, and today I'm going to be talking about Transformers work. This is my first video for this year 2024, so it's been quite fun putting together the materials for this. Transformers lie at the heart of the modern generative AI revolution, from really amazing chatbots and general purpose models like ChatGPT to diffusion models. Transformers are used in different aspects of these models to be able to comprehend, understand human language and model data in ways that was not possible before. And their invention, in 2017 is been the main reason why many of the technologies we have today in the field of artificial intelligence is been made possible. And transformers are like really amazing models, but they can be a bit like complex to understand, and it's like a steep learning curve trying to understand them. I did spend a lot of time trying to understand Transformers initially when it first came out, and put together this video as an attempt to make it a lot easier to understand and to demystify some of the more complicated parts of the neural network. First off, what are Transformers? They are basically a class of neural networks that power GPTs and other language models. So everywhere you have like a language model at work, whether it's like the language part of diffusion models that understands your text and enables the diffusion model like Midjourney or Stable Diffusion or DALL-E to then create images. Or it's just the entirety of the language model that powers like ChatGPT. Transformers, they have this unique attention mechanism which enables the model to learn the relationship between different parts of a sequence, right? So when you input in a word like it's like inputting like a sentence like I'm traveling to London. The attention part of Transformers enables you to find the relationship and importance of those words relative to each other. Like how does travel correlate with like London? How does the word I, how is it influenced by the other words that surround it, and just basically trying to like understand that in the presence of all these words in a sentence, like how does the presence of one word give new meaning to another word, right? That's why it enables them to like sort of pay attention to each other, if you can describe it that way. And there are lots of examples of transform models today. Obviously, there are like thousands of them now, and some of the most popular ones are like GPT-3 and GPT-4. Google Gemini, the text encoders of different diffusion models like, text encoder in Stable Diffusion. Some of the best computer vision models around today are built with transformers, and modern speech models like, music gen, audio gen, voice cloning softwares and models, and various like speech models are primarily powered by transformer models. So they are really ubiquitous, they lie at the heart of almost anything that's like a modern AI model, and without them, the world of artificial intelligence will not be what it is today. And to really understand transformers, let's take a look at what like a simple neural network is, right? So we said the transformer is a neural network. So what does that mean? Basically, a neural network relates one input to output as a function of a set of parameters. So in this case, we got like y, which is like a desired output, and y could be say the response you intend to get from ChatGPT. Let's say you ask ChatGPT to summarize a piece of text, so your y will be the summary, right, that you're expecting. X is going to be the input you put into the system, and where X could be your prompt, right? Maybe your prompt to DALL-E or a prompt to ChatGPT or whatever artificial intelligence system you are giving an input to. And what W in this case is the parameters of the network. So in this example, we just try to like make it very simple, like y equals to w multiplied by x. And in reality, the relationship is like a lot more complex, and the operations is like not just multiplication. There's like a bunch of operations that occur. We are going to look at some of them shortly. And the W is really the important part of the model. It's really the model in some sense, because it's the parameters that is learned from data. Like, okay, if y is a function of w multiplied by x, based on this amount of data that we've seen, based on like various texts and images on the internet, what should the value of w be? And that's what is learned, and that's the model parameters. So in reality, W is going to be millions or billions or trillions of parameters, as in the case of like hyperlarge models like GPT-4. But in this case, we have just one single parameter, so to speak. And if we think about back to like transformers, they were invented by Vaswani et al. At Google Brain in 2017. The details of that research were published in that, famous paper titled "Attention is All You Need," and you could look through that paper more. I'm going to link it in the description of this video. It's a really amazing paper, and it was primarily targeted then at like language translation, so like translated from like English to French, German to Spanish, and stuff like that. That was primarily what transformers were originally used for, but today, of course, they are used for basically everything they planet. And in transformers, everything is like modeled as language, and this is really important. So prior to transformers, we had like different models for like different things. There was like convolutional neural networks for like images, and recurrent neural networks for language, and there was just like a bunch of different models, and they handled inputs and output very separately. But with transformers, everything is like modeled as language, and it's designed to like work with sequences. So even when we are trying to like model like image, like the cute image of a cat on the left, we divide it into like a grid, and then take each single piece of that grid, each single cell in this grid as like a token in a sequence, right? Sort of, and that becomes then a sequence of tokens. So we essentially turn everything into like language, whether it's image, whether it's speech, whether it's obviously text is language, but we then turn everything to that language format, then allowing us to have a single unified architecture and algorithm that allows us model that efficiently, and sometimes, a lot of times, jointly, as can be seen in like multimodal languages, that multimodal models, that takes in like different modalities like Gemini or GPT-4 Vision, for example. And some of the key features of language data, which, transformers handle really well, is that, first of all, in language, position of words matter. So, this is some of the pitfalls of like prior models like convolutional neural networks, which don't really take into account the position of elements in a sequence. So, for example, if you have the text, the container is in the house, and you have another text, the house is in the container. So these two sentences are made up of basically the same words, but their meanings obviously are very different. And that's entirely due to the positioning of the words. So a good language model must be able to, account for positions. And we are going to see shortly how transformers do that. And also the individual meaning of words is often dependent on the surrounding context of words. So for example, if you say he's a smart student, versus he thinks he's smart, these are like similar sentences, but their meanings are like very different. This is because, the way the words relate to each other are like dependent on both position and like how the words exist in context. And this is what the attention mechanism of transformers really handle really well, is that it enables us to really understand words as a function of the surrounding words. We're going to try to understand transformers from the perspective of, the GPT architecture, which is basically a large transformer model. And we'll see how the inputs or prompts are processed and how the outputs are generated. So we are going to use a very simple example, which is given the word London is A, we want the model to complete city, right? It's just a, smart completion. And this architecture as it is like now, it might look a bit overwhelming, but I'm going to break it down into a lot like simpler parts to understand. Basically what we have here is we have London is as a prompt and we have is a city as the output, which means given London, we want to predict is, given London is, we want to predict A, given London is A, we want to predict city. And I'm going to break this diagram into two parts to make it more visually appealing and just like overall easier to understand. And the first part here is just from this London is up to this addition, which is like this half part, this first bottom half of it, coming from like top, bottom to top. And yeah, I'm going to explain this part. Now, the prompt we gave the model is London is. So what do we do? First, we take that prompt and divide it into words. And we're going to take those words and map them to a vocabulary, like tokens in a vocabulary. Now, these tokens are just numbers, right? So basically what happens is for any large language model, we've got like this large vocabulary of like thousands of words arbitrarily mapped to like unique integers. So a word like man could be mapped to like the word 100 to the number 100. The word like car could be mapped to like 50. We just like map those. We could do it alphabetically, any other ways. But the key is that we have a defined vocabulary of dictionary that takes words, a list that maps from a list of words to a list of numbers, and we could map the reverse back. Like we could take a number, fetch the word that a number refers to, take a word and fetch the number that refers to, because neural networks, whether it be transformers or whatever, only understands numbers, and our input is a string, so we need to somehow convert that into numbers before we process them. And to really understand better how this part works, this is what we call like tokenization, right? I've written up a simple Python tokenizer class that's going to like make this easier to understand. So I got this tokenizer class here, and it's just a simple Python class. It's got this a dictionary that maps from words to tokens, and here mapping London to 115, London East to 23, 8 to 55, city to 43. Again, this is arbitrary, and the way we do this doesn't matter. What that matters is that a single word be mapped to a unique integer. And now we have the reverse of that token to words, which allows us to fetch the word that corresponds to a particular token, and got just the reverse of this dictionary here. Also, we got this encode function, which basically takes a piece of text, then splits it into individual words here, and then loops over every single word, and then use this dictionary to map from that to retrieve like the corresponding number that refers to that word. So if I actually run this now, and then you will see this should give me the following: 105, 23, 55, which is basically, it's taking the word London, mapped it to 105. It's taking the word East to 23, A to 55, right? And we can do the reverse of it, which is the decoder, which is like decoding the tokens, which is we just take a list of tokens like this list, loop over it, and then convert each of it back to a word, append it to an array, and then put like a space in between them. And if we do that, let's say for example there's a predicate token is 43, we could decode that back into string, and we run that's our city, right? 43 city. So you get a concept, which is like we have some arbitrary class that maps from a vocabulary, a set of words to a set of numbers, and then can do the reverse back from those numbers back to those words in a unique way. And this is how we tokenize text, convert from like the prompt you give ChatGPT, how it gets turned into numbers that ChatGPT then process, and then ChatGPT predicts another set of numbers, which corresponds to, is the words, that's the response, and those response gets detokenized or decoded back into string before it's then displayed. So yeah, that's what happens. London is gets converted to 105 to 355, and we also take the positions of the word. So the position of London is 0, counting from 0. The position of East is 1, the position of A is 2. And so yeah, we've got these tokens in blue here, and then we got the positions right here. Now, up next, we are going to then take these tokens, each of these words, which are now, called tokens, and we're going to pass them to an embedding layer, which is going to convert from that token into a vector of a particular dimension. Here we're using a vector of 5 dimensions, and to gain an intuition for why that works, let's move over to the next slide before coming back to this. We got like token embeddings where on this side we've got like the tokens. Let's imagine that our vocabulary consists of 32,000 unique words and 32,000 unique tokens. Each of these tokens is then going to be embedded into like some n-dimensional space. So let's say we use a vector of 5 dimensions. So each single word that gets transformed into one single token, which is a single integer. That integer will then get transformed into a vector of 5 dimensions. So this embedding, lens after training is going to like assign such that it's this single, let's say token 0 now, we have the following value 0.34, 0.07, 0.56, 1.23, 0.67, 0.02, which means we can take this number and just then pick out these values in this row as the vector representing this number. The intuition for this is that when we encode London to 105, East to 23, A to 55, these numbers themselves are meaningless. Like, what does it mean that London is 105, or mean that East is 23 or A is 55, right? They are random and not unique, but random and not meaningful. But the embedding is then going to take each of these and transform them into vectors such that words having similar meaning, we have similar vectors. So, for example, if you embed, the word house and land, this vector, the values that we'll get here, if you compute like the cosine distance between them, they're actually going to, if you call like the cosine similarity between them, they are going to be very similar, in terms of like how similar the vectors are. Like they should similar words to map to similar vectors. Right, that's the whole idea of like token embedding, and that vector is going to be of a dimension, right? Here we've used 5 dimensions, which is small. In typical like GPT models, the dimension could be like 1024, 2512, or much larger dimensions. So that's what happens, and that will be done for every single token. So we'll go to 23 here, and like we'll find 23 in this position. We select all the values that correspond to it, use it as that, and date for all the tokens in our prompts. Up next, we are going to take the positions and actually map them as well. We got position 0, 1, 2. We also map them into a similar embedding space. So if the token gets mapped to an embedding space of 5 dimensions, like as it is done here, then its corresponding position will be mapped to an embedding space of 5 dimensions too. Now, the values of those will be different, of this embedding and this embedding, but it's going to be a meaningful representation such that similar positions, the positions get mapped to like embeddings that make sense based on their positions. And the embedding position encoding is also like this, where we have this table of like the position, all the possible positions that we support in our model. For example, a model of 2048 context length, we have like 2048 positions, and we have like 5 dimensions. So you could take position 1 and then just pick this vector that is length as the representation of that position. So we've got the tokens and we've got the positions. Now we've mapped each single token into a vector of n dimensions, of 5 dimensions here, and the positions into a vector of 5 dimensions each as well. And what do we do next is then we then take that and we add them up together, right? Like we add the embedding of token 105 to the embedding of position 0, the embedding of token 23 to the embedding of position 1, the embedding of token 55 to the embedding of position 2. And this represents it this way, where we have London to, for a single token London here, 105, we map it to token 105, gets embedded, and that turns into this, array, this vector array of like 5 dimensions. This is its position is 0. It also gets embedded into similar dimension space, and then we add them element wise, just simple vector addition where we add each element to one another, and that gives us a new 5-dimensional vector, that represents both the token and its position, merged up into one single entity. Now, next up, we've got that there, and that's, completes the process of like addition, right? And that addition, gets then passed into the rest of the, transformer model. So at this point now, we've gotten both the token and its position, plus added up together. And that gets passed into each of these, which is a single transformer decoder layer. So each of these represented in like this blue container is like, we pass it into, they are like identical layers. So this is identical to this. This is like a 3-layer transformer network. Now, a typical transformer network composed of like a lot of layers, maybe 24 layers, 100 layers, or whatever. But here we're just like using 3 layers. So the decoder layer here, each contains attention and a feed-forward layer. The attention layer is where, the meanings of the words gets derived as a function of the words that surround it. And then the feed-forward layer is just a layer where each of the tokens, just gets projected into another dimension. Just gets like, we learn a deeper representation, a more complex representation of it without any sort of like relationship going on. So those parts is like, this attention part is the only part where the tokens actually like mix up together. And this feed-forward layer, the tokens flow through it individually. So, and that gets repeated like 3 times. Finally gets passed into a next token prediction layer where, for each of the tokens, we pass into a linear layer that predicts then, what is the next token. So it's going to predict token, and then we can, decode that into like the word like is. So, London should predict is, London is should predict a, London is a city, is a should predict city. So that's basically it. We go from London is a, convert the tokens, positions, convert the tokens into embeddings, convert the positions into embeddings, add up the tokens embeddings and the position embeddings, and that becomes like, single vector for each token, and then pass that over into each decoder layer. At the output of one decoder layer feeds into the next decoder layer, feeds into the next decoder layer, feeds into the layer that then predicts what the next token should be. And each of the decoder layers are like, composed of an attention layer where all the tokens mix up together to like learn their relationship, and then a feed-forward layer where the tokens flow through it individually, to just learn a deeper projection of each of them, without the influence of the others. And yeah, that is it on a high level of like how, the prompt gets on from the beginning up onto predicting what happens. And this, we've already gone through this and this. And now let's take a deeper look into the decoder layer, what happens in the decoder layer. So we've already shown the decoder layer here composed of an attention layer and a feed-forward layer, and the input goes into it. And now, while all the 3 words going through, let's look at what happens when just the word London, goes through the decoder layer. In this part, what we want to do is just encode London as a function of all the others. So what we would do naturally is we pass in London into the attention layer as it's shown here. So after addition, we've gone through London, we've gone through tokens and positions, added them together, and this gives us this like maybe vector as the output of that process. And then that gets passed into the attention layer. So we pass that into the attention layer, but because in the attention layer we want to consider the other words surrounding it, we're going to also pass in the word is and a, all the other words into, and just pass them into the attention layer, and that's going to learn. And that's going to then be used by the attention layer, which I'm still going to explain of how actually, it does gets like added up and like, like the other relationship gets learned. And it's going to then produce another representation that's still going to be of the same dimension as the input, but this time around the values will have been transformed based on the words that surround it. And that gets the output from that then gets passed to the fully connected layer, which then gives another transformation of the input. Now notice something, it's only this attention layer where we pass all of them together in there. Like in the fully connected layer, the word London, just the output from that attention layer just goes straight in there, right? Because each individual words will flow to the fully connected layer individually, while the attention layer is where all of them, gets mixed up. We look at the same thing for the token is. We've got like, token is goes to addition, then the output of that gets passed to the attention layer, then we feed in the output from London, and A, we feed that in as well, and it goes to the fully connected layer as well. So it's quite same process. And we can look at A as well. Token A is just, goes to the same thing, and we take is and London, pass that into its attention layer, and then pass it the output from that into the fully connected layer. So that's basically what happens, right? It's just like each of these flows through the attention layer and they get mixed up, and then they individually go through the feed forward layer. Now, looking at all of them together, it forms like this rather, interesting and complex diagram where, all of the inputs flows through each other's attention layer, and then they all individually go through this fully connected layer where, the output of that then gets passed to the next decoder layer. Like the output of that process gets passed to this next decoder layer where the same thing happens again, and then gets passed to another decoder layer, the same thing happens again, up until how many decoder layers we have. And then at the end of it all, we just have a linear layer on top that then does what's the next token, right? Giving all this complex representation that has been learned. In the next video, I'm going to be talking a lot more about the attention layer and the feed forward layer and how they work internally, like how the model actually learns to, relate different inputs to each other in the attention layer, how it, encodes these meanings, and ultimately it leads to this whole magical outputs that you get from like ChatGPT and all the amazing models out there. Thanks a lot for watching this video. Looking forward to sharing the next one with you, and as always, please subscribe to this channel and post your comments in the comment section, and I'll be happy to clarify, share any thoughts that I've got, or answer any questions that I can answer. Thank you.